Bless you.
Alright, so hope you all are doing well. Welcome to day 11 of our decal. Today we're going to be covering decision trees and announcements. Project 1 is due Friday at midnight. I'm getting a sense here that all of you have finished, but for those of you watching at home, if you haven't started, you should really do that soon and just make sure to get it in by then. Okay, so with that being out of the way, let's dive into the lecture today. So just a quick agenda. We're going to look at one, logistic regression can fail. We're going to be looking at the game, 20 questions, basically, and going over a new kind of classifier called a decision tree, and that'll be the subject of today's lecture. So let's get started with logistic regression. So basically, it's, we have some dimensional we're doing a classification problem in some number of dimensions, right? And as a result, we have some linear hyperplane that'll classify our points. Those on one side are red, those on the other side are blue. Cool. But, in reality, not all of the decision boundaries can be so nice and linear. Sometimes you have these rough jags and edges, and it can be very hard to actually classify them using some sort of line. And today, the point of lecture is going to be discussing a tool that'll help us get around that. But before we really get into it, just a show of hands, how many of you here have played the game 20 Questions? Okay.
What else do you do on long car rides?
Okay, so basically, for those of you who haven't played, it's basically you try to think of a person, name, thing, animal, or whatever, and you're allowed to ask 20 yes or no questions until you are able to correctly guess it. So here you can see an example of someone thinking Cinema Bizarre, which is a band, and so through these questions, they're able to more and more narrow it down. And let's actually draw that out on the board. For those of you watching at home, I'm going to be taking pictures and posting them up alongside the slides. So I'd advise you to have those out while watching the rest of this lecture. So right now, starting at the very top, we have anything. We have no idea what our thing could be. So our first question, is it a person? Yes. So we have person, not person. Our second question, do you have tattoos? Yes, so tattoos. Not tattoos. And you can see how basically when we write out the state space of this, basically it's, we're slowly but surely reducing our state because anything... let me just annotate right here. So yes, no, yes, no. So you can see how for our first question, right, anything that's on the right side of our tree, not a person, we can just ignore that because that's not really relevant. And then, we know that they have tattoos, so not tattoos becomes irrelevant, and we can just do this more and more, and you'll notice that this is a tree structure, right? We start with our root, and then we have 2 branches, and each of those branches has 2 more branches, and then, eventually we go down, and then you have at the bottom, is it Cinema Bizarre. And so, this is going to be a leaf in our tree, right? There's going to be no more branches. It's just one singular thing that we've managed to reduce it to. And that's how, we played 20 questions in the form of this decision tree. Does anyone have any questions? Yeah.
Are decision trees always binary?
They don't have to be, but basically, like, implementing non-binary ones can be pretty tricky. Implementing decision trees in and of themselves are a tricky thing, so we're just making it binary to make our lives easier. I'll actually go through a non-binary example just to like give you some intuition, but generally they are implemented as binary. All right, so I'm just gonna take a picture right now. Okay, so yeah, anyone else have any questions on 20 questions and how we're representing it? Okay, so let's move on to a scikit-learn example. So, one of the data sets that we've been giving in a lot of our like practice IPython notebooks is the iris data set. And so, recall that there are 3 different classes of flowers: Setosa, Versicolor, and Virginica. So we are now going to play a game of 20 questions of sorts with these flowers. So we start here at the root, and here we have all of our possible flowers. We have 150 of them. And so the first question we're going to ask is, is our petal length less than or equal to 2.45? If so, then we know that it must be a setosa. All of the setosas have petal length less than or equal to 2.45, and if so, we're done. There's like 50 samples, as you can see over here. And then but let's say that's not true. Now we have 100 samples, and we want to see, is our petal length less than or equal to 1.75? And if so, then we break into 2 different branches over here, and then we just keep going, so on and so forth, because, all these questions are like yes/no questions, so we could play a game of 20 questions with this data set. So hopefully now you get a sense of, basically what we're doing is we're taking a feature from our data set and we're using that as the basis of our questions. But the question then arises, how do we ask questions? So which questions should we pick for our decision tree? So at a high level, we basically want to come up with questions that allow us to split our points the most. And, usually that's like, and so typically when we do this, like for our features, we're just going to pick like the median value of that feature. If it's discrete and if it's like categorical, we could either one-hot encode it or just make a separate branch for every possible value of the feature. But again, we have to figure out which feature do we split on. Does anyone have any questions on the example I did / where we are now? Okay, so how do we pick which feature to split? So the way we do that is through this tool called gini impurity. And essentially what gini impurity is so suppose that we just have like a bunch of different like data points with different features and different labels. So gini impurity is a measure of like, if like, let's say, going back to this flower example, let's say that I have like 5 setosas and 8 versicolors. So I want to figure out like, okay, so if I just chose like a random flower, knowing that I have 5 setosas and 8 versicolors, how likely am I to make a misclassification. And the way we actually do that is through this formula. So what we do is we would take the frequency of each class. So, we have 5 over 13 setosas, 8 over 13 versicolors, and we would take the sum of all those frequencies squared and do 1 minus that, and that would give us our result. Now, to give some intuition as to why this is, let's imagine that instead we had only setosas. So in that case, our frequency would just be 1, right? Because 5 over 5 is 1, and then 1 squared would be 1, so then we're doing 1 minus 1 is 0. So what that tells us is, okay, we have no ambiguity, right? We have no sort of misinformation, okay, there's only one thing it could be, a setosa. Great. Now, on the other hand, so that's the best case. 0 is the best possible gini impurity we could have. No impurity. But conversely, let's say that I had n different classes and n samples, with each sample being from a different class. So in that case, our gini impurity would be n minus 1 over n. And if we take the limit as that goes to infinity, then that approaches 1. 1 is the worst possible gini impurity we can have. And hopefully this makes sense to you, because intuitively, let's say that I had 2 samples from 2 classes. So, imagine you're taking a test, a multiple choice test. You had 2 different choices you could pick. Okay, 50-50. That's not too bad. Let's say I had 3 different. 1 and 3, slightly worse, but not terrible. But let's say I ramp that up all the way to 100. You're definitely likely to feel less confident about your choice, right? Because there are so many other choices it can be. So, as n goes to infinity, you have more impurity. Again, 0 is the best, and 1 is the worst. Does anyone have any questions? Okay. Slides are a bit... Hold on. Okay, so let's say that I have this example right here. So here I have a set of 20 different people, and we have 3 different features: gender, car type, shirt size, and then we have their class, either class 0 or class 1. So if I wanted to calculate the gini impurity of this set, so if we actually go through and count the number of different people that we have, up until 10, they're class 0. Up until 20, they are class 1. So each of the frequencies is 1/2. So, it would be 1/2 squared plus 1/2 squared equals 4. Equals 1/2, right? Hopefully that makes sense to everyone, just taking, because each of these classes had a 1/2 frequency, and so we just square each of those, add them together, and we are left with 1/2. And so now let's actually get into decision trees. So the goal with doing gini impurity for decision trees is to essentially say, okay, so recall that with 20 questions, we took we made some sort of split. So right here we have person, not person, whatever. So, and then going back further to our setosa example, our flower example, we have these different sets of flowers. So we want to make the split such that what we end up doing is the average of the gini impurity of our children is less than the gini impurity of the parent. So, and basically what we're going to end up doing is for every feature that we have, we're going to split it. We're going to use that as our splitting point, check and see how it does, and whichever feature has the highest reduction in gini impurity, that's the feature we're going to pick. Does anyone have any questions on that? Yeah?
How do you recalculate the gini impurity after you split?
Well, so it's like we don't actually make the final split, right? We just want to see, okay, what's the gini impurity? If I make this split, we don't make it. We do it like for all of our features, and then based on those, we just keep track of which one has the best, and then we make the split. Because yeah, we can just split them, combine them, split them, combine them. We're not committing to anything until we look for all the features. Does that make sense? Okay. Yeah?
For the previous example, can you just prove again how the gini impurity is 0.5?
Sure. So if we go back to it here, so we have 10 examples of class 0, right, and 10 of class 1. And so the formula for calculating the gini impurity is we do the sum of the frequencies squared, and then we do 1 minus that. So we're doing 1/2 squared plus 1/2 squared is 1/4 plus 1/4 is 1/2. And I didn't write out the last step, but then you do 1 minus 1/2 equals 1/2. Does that make sense? And then, yeah, I think you first, then you had a question? Or yeah, okay, yeah, you. What's your question?
So when you do this splits, do you go all the way down or just do one level down?
Like, you mean when deciding which feature to use? Oh, you only do one split at a time. You're doing it in a greedy fashion. This isn't guaranteed to produce an optimal result, but it's a good heuristic. So yeah, we're just assuming that whichever feature we pick will be the best one, even though that's like not the actual case. Yep.
Give me an example of like how you could split it in and what would the gini impurities look like after you split?
We're actually going to be diving into that right now.
Okay.
Yeah. So with shoot, what is wrong with my computer? Okay, so yeah, so we're going to be going back to this example once more, and we're going to be using it to calculate. We're going to be actually doing a decision tree on it. So I'm going to get rid of this right now, and we're going to replace that. So we have 3 different features that we could pick for our first split, right? Gender, car type, and shirt size. So the first thing we're going to be doing is we're going to start with the gender feature. So split 1, gender. So we have 3 different, so we see that among our male data points, we have 6, which are class 0, 4, which are class 1. So we have 0.6 times 1 minus 0.6 plus 0.4 times 1 minus 0.4, and that's equal to 0.48. Oh yeah, and so actually what I'm doing over here is I'm taking each frequency, multiplying it by 1 minus that, and adding them all up. That's actually equivalent to summing the frequencies and then doing 1 minus that. So that's why like now when I have this 0.48, I'm not doing the 1 minus that. So and then for our female data points, we have the same split. So 6 and 4, so then that'll be 0.48 also, so 0.5, so then average reduction equals 5 minus 0.48 is equal to 0.02. Now, let's try with car. So if we look at the sports cars, we know that all of them are class 0, so the Gini impurity for that class is 0, much like how with our plant example, when we made the first split, all of our examples that were setoses were just put in their own leaf, so we're doing the same thing here. So for cars, sports, no, I should say 0 Gini, 0 Gini impurity. For luxury cars, we have 8 class 0s and 1 class 1, so that is 0.88 times 1 minus 0.88 plus 1 minus 0.88, 1 minus 0.8. Two, one, one, two. Okay. Yeah, apologies for the latency of the slides. Alright, so, and now we have our shirt size. So here we have more classes, so we're going to break it down.
Is this supposed to be?
So we have our small. So for our small case, we have 5 examples, 3 of class 0, 2 of class 1, so that comes out to 0.48. 7 examples, 3 of class 0, 4 of class 1, 0.489. 2 of each, so 0.5 again, and 2 of each again for extra large, so that's 0.5. So if we write that out, small, 0.48, medium, 9, large, and then yeah, 5. So now what we need to do is we need to put all of these together. So if we look at how many of each we have, so we have a quarter of them small, 7 out of 20 medium, a fifth of them large, and then a fifth of them extra large. So if we take the weighted average of these Gini impurities, then that comes out to 0.49115, and then we do 0.5 minus that to get 0.0088. And then if we look at the 3 different Gini impurities, we see that 0.2112 is the greatest, so that's the feature we're going to be choosing for our first split. So does anyone have any questions on what we've done so far? / can you see why it is that for our first split, we're going to be choosing car based on the calculations that we've done? Okay, so yeah, I'm just going to write this out here. So
then do you remove like cars from your feature set and then you just do the decision tree on whatever's left?
Yep. Yeah, I'll be getting to that when we do our second split. So is a entry sports car. So yeah, so as you can see over here, this is what we're doing for our first split. So let's move on to our second split. So now as a result of the above, we see we have 3 different nodes. All the sports cars are class 0, so we're, oh yeah, and I also forgot family car, so let me actually write that out better. Family car, sports car. So remember above we calculated all the sports cars have gini impurity 0, so now we're only concerned with luxury and family cars, so we need to look at each of these over here and determine which will work best for our second split. So we're going to be breaking this down into family and luxury car. So if we look at family car, we notice that, so I'm going to be writing over here. So can everyone see if I go all the way over here? So second split. So we know that all the family car drivers are male, so we can't really split on that. So let's look at the shirt sizes. We see that the only family car driver that is class 0 happens to be the only small shirt. So this person is immediately put in their own class. So are they small leaf? And then, and that's the same as do the large medium with 2 extra larges in one class. So basically, medium, large, so yeah, and as you noted, there's no point splitting on the car size anymore because we have all of them in the same set. So that means we're done splitting for that node. Now let's look at luxury. So let me write that slightly higher. So for gender, we have 1 male luxury car driver and 7 females. So if we calculate the so 6 of class 0, 1 of class 1, so that gives us a gini impurity of 0.244. So for shirt size, so shirt shirt size, we see that the small, medium, extra large become leaves because all the people who drive them have those shirt sizes are class 1. And then the only remaining impurity comes from the large group where we have 2 females who are either class 1 or class 0. So we have an impurity of 0.12. And at this point, we just have a random chance since both data points are the same feature but different labels. So we can actually see that if we go back, assuming my computer will let me do that. Okay, shoot, I can't go back right now, but if you actually look at the data set yourself, you can see that there are two like examples that have exactly the same feature but just different labels. So we have like no way of actually being able to make. Oh yeah, here we are. So let me see if I can pull the example up for you real fast. Female. Yeah, so if you look at female, luxury, and large, examples 10 and 20, you can see that they are exactly the same but have different classes, so we have no meaningful way of actually being able to classify that. So does anyone have any questions on what we've done so far in our decision tree? Anything unclear about any of the math or like how we're picking the features that we split on? Okay. So if we go back here, we can just label this is a leaf, and then so for family. Okay, so if now taking a step back, we see that decision tree produce very nonlinear decision boundaries, and hopefully that makes some sense, right? Because as you can see in these two pictures over here, we're like slowly bisecting our region into different chunks, whereas linear classifiers such as like logistic regression will just like chop up like a bunch of stuff at once. Okay, this half of the hyperplane is class A, this is class B. And so sometimes that can work well, right? Like if you look at the bottom example where we don't have a linear decision boundary, this can be perfect because you have these couple of nice chunks that can just be bisected nicely. But if you look at the top picture, it doesn't work so well because our decision boundary is perfectly linear, and so doing this nonlinear, like piecewise chunk breaking up doesn't make all that much sense and can lead to a bunch of misclassification as opposed to the regular linear regression case. Does that make sense to people? Yeah?
But then, doesn't this like really overfit to the data set?
Yeah, I'm actually going to be getting into that next. Yeah, so we're going to be going over some ways that can help decision trees not overfit, because yeah, as you noted, like it can be very easy for this to happen. So some of the problems our decision trees with, as you noted, we overfit because sometimes, in many cases, when we have leaves, we can often just have one entry in it because our rule is, okay, we don't stop until we have no gini impurity. So once we have and that often only happens when we just have one example. So in that case, we are heavily overfitting, and that can be a real problem. We don't want to overfit. So there are some ways around that. And so, yeah, this just, again, notes like specifically hardwired to recognize certain patterns. So there are a couple different ways of stopping this, and one way is to force some stopping rules. So for example, one thing we can do is limit the depth. So like over here, as you know, over here we have depth 1, here we have depth 2, and here we have depth 3. So we can enforce a rule that says, okay, once we go so far down, we're just going to stop. And essentially then what we'll do is, given the examples that we have, we can just say that, okay, we'll look at the probability that it's any given class and just, take the class that's most likely to be. So let's see this next slide. I'll have this picture here, right? So here we have 3 different leaves, and so here in this case we're going to predict this green one because it has the highest probability, and this gives us an advantage like logistic regression. We can output prediction probabilities to really see how well we are actually doing. We could technically, of course, do this in the case where we just have these, like where we have our regular decision tree, but in that case, since by definition we have no gini impurity, then we are just going to have a 100% probability, so that doesn't really tell us too much. This can be a lot more descriptive. And another way that we can actually prevent overfitting is to have an impurity threshold. We say, okay, if there aren't any features that help us reduce our impurity by more than a certain amount, then we're just going to call it good, and then similarly to our depth cutoff, we're just going to say, okay, all these things here, that's a leaf, and then when we predict, we're just going to take whichever class has the highest probability, and we are going to call it a day for that. So there's actually another way that we can get around this in addition to thresholding, and that's called pruning. And so unlike in the previous techniques where you just stop right away, you actually grow the decision tree out completely, and then what you do is, like the name implies, you cut off branches that prove not to do so well, and you measure that by doing validation on your validation set. You can see, oh, okay, if I don't have this branch, my validation accuracy goes up by this much, so this branch was bad, we should remove it, or similarly, oh, this branch turned out to be really good, we need it, we should keep it. And sometimes what you can have is good splits which are locked away behind seemingly bad ones. So it can be advantageous in order to do that. But a downside to this is that it's more complicated than the others. And if you actually look at the scikit-learn decision tree, they don't actually implement this. They just implement the other 2 techniques that we discussed, impurity thresholding and depth thresholding. So we're going to keep the discussion of this technique somewhat more cursory, but I just wanted you to be aware that it exists and is another way that we can prevent overfitting. So does anyone have any questions on what I said about how decision trees can overfit and the techniques that we've discussed to prevent them? Okay. All right. And so lastly, we have, okay, so I'm just going to explain this. We have another problem of decision trees, which is that they can be very high variance. And essentially what I mean by that is, suppose that I take my decision tree, or I took my data set, split it into 2 halves, and trained separately on those 2 halves. We could have very different data sets, especially if a different feature is picked for the first split. And that means that decision trees can be very unreliable. And to give a sort of analogy of that, let's say I flip some sort of biased coin, which essentially means that it's not always 50-50 like you'd see with a regular coin. And essentially what you're doing, let's say I just flip that coin one time. I say it's heads. Okay, so you could say from that, oh, it's more likely to be heads. That could be false, and that's because, if we just take one sample, that's not a very reliable estimate, much like with this decision tree. So any individual decision tree could be very unreliable. We're not going to go into the fix for this problem in this lecture. That's going to be the subject of next Monday's lecture when we get into random forests. And there that'll actually give you the technique to solve this problem, but it's something good for you to think about how you might try to go about fixing it. Like, think about the analogy that I gave you with the coin. And that's all we have for today's lecture. Wait, do we have the quiz app? Okay, could someone make that real fast?
Yeah, I have to talk about something real quick.
What do you have to?
About the project.
Uh-huh.
How to submit.
Oh, okay.
And then also we could do a
All right.
live demonstration of.
Okay.
Okay, cool. I'll just study for a while. Gosh, what is wrong with your computer?
That's a very good question.
Yeah.
I'm going to investigate after this, but yeah. So actually, does anyone have any questions about anything covered in lecture thus far? Okay, cool. All right. In the meantime, I'm going to be taking pictures so we can put them up for people.
Mhm.
With chat.
And in the meantime, I'll wait for your. Okay, there we go. Where's Slack on here? Because I sent an example to the Slack. So basically, when you're submitting files to Kaggle, you want to submit in the form of a CSV, and the first row is going to be your header, and the first column of the first row should say wine _ID, and the second column should say label with all lowercase letters. And then,
And it should start
and I
with
mean,
0.
it's not that hard. Yeah, huh?
ID, the first ID should be
Yes,
0 or
ID, it
1.
should be 0 index. Wine so wine is all lowercase, and underscore, then capital I, cap D, and then label, not labels, just label, and all lowercase.
If they go on the Kaggle portal, they can download a sample submission. So you can just can see it.
You can, or it goes back, it keeps going back to just the data.csv. I think you have to upload that.
Sample submission file? I uploaded
Yeah,
it.
well, oh, you did?